So my research covers a whole range of issues to do with active visual cognition in different populations, as was mentioned, sometimes adults with autism, and more recently a lot of developmental work, eye tracking of infants and the development of ocular motor control and scene perception. But today I'm going to be talking about an issue which stuck me when I started doing eye tracking research in scene perception, in that the majority of what we know about scene perception and how we move our eyes and attend to a visual scene actually comes from studies looking at photographs. So there's been a lot of interest recently about going out into the real world, doing kind of active visual tasks in fully mobile situations. But there's also a kind of a in-between step, which is when we can look at how people attend to real-world scenes that actually are captured and move in front of them on the computer screen. These are the kind of scenes that we might see if we're actually looking at a visual scene in everyday life, or if we're watching TV and film. And there's been very little research up until recently on how we actually attend to and make sense of scenes like this. So in some of my earliest research, we started eye tracking people looking at scenes, either moving scenes or static scenes. And something is immediately apparent when you actually get the gaze data of people looking at video scenes compared to photographs. If we eye track people, here we've got the gaze location of 7 people looking at the photograph of the scene, and there are certain parts of the scene, like the boy on the swing, that are preferenced by gaze. People keep coming back to it. But there's a lot of variance in where people attend and when they attend them. But this kind of variance goes away as soon as you make them scene move. So people are just free viewing this scene, and spontaneously you get this coordination of their gaze. So you all seem to be preferencing the same point. And we call this behaviour attentional synchrony. Now it occurs irrespective of the content of the scene or the way it's composed. If I look at feature films on TV, we're going to have a greater degree of attentional synchrony, coordination of gaze, than if we have a natural uncomposed sequence. But still, in these uncomposed shots, we'll have a lot more coordination of gaze than we do in a static scene. So what I'm going to be talking to you about today is what factors may actually be driving this attentional behaviour, and also see what factors are influencing the decision about where we fixate when looking at dynamic scenes like this. So I'm going to give you a little bit of background on how we're approaching this question. So any of you that are familiar with visual search or basic attentional literature will know that often we talk about two interacting factors that are influencing how we make the decision about what is attended at a particular time. We can refer to these as exogenous factors. Exogenous are the external, bottom-up influences over our attention. It's what's in the actual visual stimulus itself, and may command us universally to shift our attention to a point in space. So if we were searching this array here, and our task was to find the L amongst the T's, if the L was a different colour compared to the T's, it's going to be very easy for us to find it. And also, it doesn't matter how many distractors we have, we'll still find it as quickly because it's going to pop out, it's going to capture our attention. Now, this is exogenous control of our attention by the colour difference in the image. Endogenous factors are those which are top-down, internal. They're voluntary, they're driven by factors such as task, expectations, memory, and familiarity with the stimulus. We have to actively make a decision about what's being attended at every point in time. So if we were searching this array down here, and there are no visual features that make the actual target pop out, as the number of distractors increase, or the complexity of the scene, it's going to take us longer to find it. We have to make the active decision about where to attend. And we can look at how these two factors interact in the classic visual search paradigm, and we're going to look at them in dynamic scene perception. So what is currently known about how these factors influence our gaze behaviour in static scenes? Well, going back to some of the very earliest studies by Buswell and Yarbus, it's been known that actual task instructions can have a big effect on which parts of the scene you choose to attend to over others. So you will have all seen this before, I don't need to explain it to you in too much detail, but when looking at the Rapin painting, The Unexpected Visitor, people will attend to different parts of the image, such as the people's faces, if they're told to describe the age, or they will look around at objects in the scene if they're told to remember where the objects are. So we are choosing where to distribute our attention due to endogenous factors. The flip side is the influence of exogenous factors on our gaze control in scenes. So these are classically thought of or formalized in terms of the idea of visual salience. When we've got an image of a visual scene, we compute from that a saliency map, which is a probability distribution of how likely we are to attend to a point in the actual space. And this is thought to be computed bottom up from the visual features. So we use luminance, colour, edge information in a static scene, and these are weighted together to create a probabilistic map, and the point which has the highest salience is the one that's thought to capture our attention. In a study looking at this in photographs, I showed that if you take a scene like this, where we've got an object that you can barely see, which is this bowl, and according to any saliency map, this has 0 salience. There's nothing visually discriminating this from any other object in the scene. If you look at the probability of fixating this bowl when they're just memorizing the scene, it'll gradually increase over time. But if I boost the salience by making it incredibly luminant, and the luminance is incongruous with the background, its salience increases, and the probability of fixating it increases here. So that by the second saccade, you're more likely to fixate the highly salient bowl than you were without it being salient. And the same happens if you're just freely searching, or if you're searching for the bowl without the salience and then with the salience. We can drive attention to it if what you're looking for is also the most salient thing in the scene. And this relationship between visual salience in static scenes and areas which are fixated, typically during a free viewing task, has been shown by various people. The largest and most known proponents of this is Laurent Petit and his colleagues, where they can create a computational model of how you actually attend to a scene just based on bottom-up features. But, as is obvious from the Yarbus example, the stimulus itself does not always guarantee that we're going to attend to it in the same way when we're talking about a static image. Task seems to have a big effect. So in this variation of the experiment, we looked at what's the probability of fixating the bowl versus a distractor object. Here it's a spoon. If we make the bowl salient, then you're significantly more likely, this blue line here, of fixating the bowl than you are the distractor item. Your attention gets guided to it. But if I make the distractor salient, and you always know that the distractor is going to be the salient object, and you're searching for the bowl, you're no more likely to fixate the distractor than you are the actual target object. So knowing your viewing task and knowing that salience is irrelevant means you can completely override its influence on your gaze. And similar demonstrations of this effect of endogenous overriding exogenous factors have been shown by Henderson and various other people. So it seems that in static scenes, the actual influence of the visual features seems to be minimal. An actual viewing task and your interpretation of the scene seems to be most important for guiding our attention. But given that we see the difference in the gaze behaviour in the static scenes versus the dynamic scenes, where we've got the attentional synchrony, a lot more coordination of gaze, it could be the case that actual exogenous control is more important in a dynamic scene than a static scene. So this is what we're going to go into detail and investigate across a series of experiments today. So we're going to first look at visual features in a dynamic scene at fixation, and then we're going to present a study where you manipulate the actual task and see if that can change your viewing behaviour. Then we're going to look at whether we can actually dissociate the causal influence of visual features on your gaze, and if we get time, I'm going to look at the role of expectation and your interpretation of what's relevant on your gaze location during magic tricks.
They should
So to
induce
begin
a
with,
warming sensation, reduce some of the pain, and also reduce the inflammation so it works.
I'm going to briefly summarise what we know already about
200 grams
the
of cheese.
actual correlation between salience in dynamic scenes and where you fixate. This is a video that comes from the DM corpus, which is a publicly accessible corpus of eye movements of people watching videos. TV clips, video clips, film clips, music videos, adverts, a whole range of things that we actually collected over the last 5 years we got a large number of people watching these video clips. For some of the clips, including this one, we have over 220 people watching it. Gaze recorded on, I think, 1,000 binocularly. And this was just a free viewing task of a whole range of video clips, because we wanted to see what kind of variation in gaze behavior we get when watching videos like this. And what is evident in all of the videos pretty much is the same kind of clustering behavior that we saw before on the playground clip. That here, for the majority of the viewing time, your gaze only occupies about 6% of the screen, and everyone is reacting to the content in the same way. So in the DM project, one of the analyses we did to begin with was to actually see if we could relate the fixation positions to the visual features in the actual scene, in this kind of saliency approach of computing the relationship between visual features like luminance, color, edge information, as well as dynamic features like flicker and motion, to see whether the increase and the presence of dynamic features in the scenes are predictive of gaze location when looking at videos like this. So a similar approach has been taken by various people, including Laurent Itty, where they've used the dynamic features to compute dynamic saliency maps and generally shown that the predictive ability of dynamic saliency maps is significantly greater than it is for static saliency maps. So when you compare the gaze behavior in a dynamic scene to a static scene, it becomes a lot more predictive in a dynamic scene. And in our analysis of the DM data, we were able to confirm this kind of relationship by, instead of computing a summed saliency map, we look at the individual contribution of particular features in the video scenes. So here's an analysis that we published in 2011, where for every frame of the movies, we take the digital image and we decompose it into separate visual channels. So we can identify the luminance of that frame, 2 different color channels. We've got red, green, and blue, yellow color channels. And then from that, we can identify certain visual features that are believed to be neurally plausible in terms of processing in the early visual system. We've got edge information, we have oriented edge information, which are these balls down here. And then we have corners and dynamic features, which is flicker, just change either from one frame to the next in terms of luminance, or over 5 frames, and optic flow, which is a coherent movement of the pixel values in space and time. We can actually see the image flowing, and this is our proxy for motion. And throughout the video clips, we're able to compute the likelihood of distinguishing the fixated locations from a sampled control location, and do receiver operator characteristics on this, which gives us a value between 0 and 1, showing how predictive the actual individual visual feature, like luminance, is of the fixation location. If it's close to 0.5, it means that that feature alone is not predictive of your gaze location. The closer it gets to 1, the more predictive it is. What you can see here is the basic features, like luminance and the color channels, have very low predictive ability. As we go up and get more complex features like edges and oriented edges, they become more predictive, but by far the most predictive are these dynamic features, the optic flow, both in the horizontal and the vertical dimension. So by knowing where the motion is in these videos, as in the playground clip where we knew that the boy was swinging on the swing, if we know where that is in the image, we've got about a 70 to 75% chance of predicting where you're likely to attend at any particular moment when watching the movie, without knowing anything else about the actual content of the scene. And you can see how powerful motion is if we strip everything else away and we just give you the motion. So this is our motion detector, and we've taken the values which have been identified for optic flow, and we've revisualized it in terms of a heat map. So the points which are darkest red are those which have the highest motion, and the blue are the bits with no motion. Now, looking at this, all you're seeing is the motion in the image. This is an edited video clip. Can anybody tell me what action is depicted in this? It's a type of TV program or event. Okay, So we've just cut to a new shot. We've got motion down here and motion up here, and they're both running backwards and forwards.
Tennis.
Yeah. So this is the classic way that you would actually film tennis. So this is a close-up of one of the players. He's about to serve. He serves across the line, and the other person runs around, and then they run around and knock it backwards and forwards. And this is just the motion. If I show you the gaze behavior of people watching the same clip, you can see that the majority of the time, the points that they're fixating are the points that were also of highest motion. So this means that we have high predictability just by taking a sequence like this, finding the motion, and therefore using that to predict where people are likely to look. But of course, all we've actually shown is that there's a big correlation between the motion in the video and fixation location. We haven't actually shown that the motion is causing people to look there over somewhere else. It may be the case that actually the motion is correlating with other features, probably mid-level or higher order features of the scene, which are more important in terms of deciding where we're going to look in the scene. In a lot of these clips you can see here, it's people's faces, it's people's hands, it's their bodies. In the tennis clip, it was the people, and you're watching tennis with the purpose of watching the players and whether or not they win the point. So there's going to be a big correlation between your semantic interpretation and your expectations of the scene and the visual features at the low level. So to really get at the role of visual features in gaze guidance in visual scenes, we need to have a way of actually teasing these different factors apart. So how can we dissociate endogenous control from exogenous control when looking at dynamic scenes? Well, there are two main approaches. In terms of manipulating the endogenous factors, we know that during free viewing of film clips, like in DM and all other previous studies that have looked at predicting gaze location in dynamic scenes, it seems to be that we can predict it just based on motion. But what about if we manipulate the task? What if we do a dynamic Yarmouth? We simply give them a viewing task, which should preference them away from the dynamic features. If their attention is under exogenous control, they shouldn't be able to divorce their attention from the points of high motion in the scene. It should continue to capture their attention. So can we manipulate task to change gaze behavior? And this is the first study I'm going to show you, which is the spot the location task. And then the other approach we can take is try to remove the visual features in a film and see how that changes our viewing behavior. So we know that motion predicts gaze behavior in dynamic scenes, and saliency overall predicts it better than static scenes. So what about if I take away the motion from a movie? Now that might seem a bit bizarre, but I'll show you videos later to explain how we do it. And that's the knockout study. Okay, so to begin with, task effects on gaze behavior in dynamic scenes. Quite surprisingly, no one had done this, well, fortunately for me, up until last year, but it's okay, they did it wrong. This was a study by Taya, Winrich and Osman, and they got people to watch, rather coincidentally, video clips of Wimbledon, and they either told them to preview the clips or to watch the clips and try to figure out who won the point. They then did a whole range of eye movement analyses, basic oculomotor measures, as well as the variance in the gaze location. And they found nothing in the actual eye movements. If you asked people which part of the image they attended to in the two different tasks, they said they were attending to different parts of the image. But if you looked at their eye movements, they were attending to the same places, they had the same fixation durations, they had the same saccade amplitudes. There was no identifiable differences in their gaze behavior. But the obvious problem with this is that by giving someone videos of tennis and telling them to preview it, the main objective of watching tennis is to see who won the point. So these are not different tasks. They haven't given them a task which preferences them away from the dynamic features of the scene. So their task manipulation has been ineffectual. So in our version, we gave people natural scenes like this, including the playground scene you saw before, and they were told to either free view the scene, or they were told to see if they recognised where it was shot. Now we did this in Edinburgh, and we filmed all these locations, either in very famous locations or in not so famous locations in Edinburgh. And as soon as they thought that they knew the location, they pressed the button, and the scene continued for the full 20 seconds. Now we did this both with static photographs and dynamic versions of the same scene, where the static were frames that we took from the video. So we could look at the differences across static dynamic and the influence of the task. So we could do a cross comparison. We had 24 participants, 28 participants in 26 scenes. So to begin with, what effect does the viewing instruction have on your oculomotor metrics when looking at these different scenes? Now, a little note I want to put in here. Has anybody here eye-tracked anybody watching videos or any dynamic scenes at all? Naturalistic scenes? No? Okay. If you were to do this and you were to do it on the eye link and you were to run the normal eye movement parsing algorithms, you would get this, which is an incredibly jumpy eye movement. This is a smooth pursuit we see right here, but eye tracker can't handle this because it has assumptions that your eye movements are parsed into a series of fixations and saccades. If you have smooth pursuit, the assumptions are invalidated and it misrepresents your data. It actually creates phantom fixations that aren't there. So when you're doing this analysis, you need to go back to the raw data, which is here. This is the raw data per frame of the video, and you need to look at the actual velocity dynamics to see that you can separate out smooth pursuit movements. There are various ways to do this. One algorithm that's available is the Mark-I algorithm by Birkbeck and colleagues. You can also do it by just excluding low velocity movements. If we do this and get rid of this potential smooth pursuits, we can look at fixation durations and saccades in our scenes. So looking at the mean fixation duration, we look at the static first. In the free viewing condition, they had a mean fixation duration of about 280, 290 milliseconds. When they were doing the spot the location, which is essentially a search task, they're much quicker. And this confirms in many previous studies the influence of search on fixation duration. We get the same trend in the dynamic scenes. You're much quicker when you're searching the scene than when you're free viewing it. So we've already changed the basic metrics in a way that Osman and colleagues did. We also get a significant effect of dynamic scene that you tend to fixate for longer in dynamic scenes than you do in static scenes because there's actually more happening at each fixation location. In terms of saccade amplitudes, when you're searching a scene, you make longer saccades on average than you do when you're free viewing it, again confirming classic task manipulation in static scenes. We find exactly the same effect in dynamic scenes. So we've got a similar effect of task on the basic measures in dynamic scenes as static. But to confirm that we've still got the actual attentional synchrony that we saw during the free viewing, we can look at the clustering of the gaze. Now here we've used an overly complicated method called Gaussian mixture modeling, which will fit the optimal number of clusters to our gaze for every frame of the movie, and it will express them as a covariance. The covariance basically says what proportion or what visual angle is occupied at that particular moment by the gaze. So you can see it's represented as this heat map here. In the dynamic free viewing case, everyone's looking at the boy on the swing. In the same frame from the static free viewing, there's much of a bigger variance of where they're looking. And this is represented here, where static free viewing is here. There's blue point, where they've got much bigger variance in their gaze, and dynamic free viewing is here. So they're much tighter in where they're actually looking when they're looking at the dynamic versus the static version. If we change the viewing instruction, it has no effect in the static scene because they're already looking all over the place anyway. But in the dynamic scene, it significantly decreases the actual attentional synchrony, which means that there's more variance in their gaze. So we increased the range at which they're looking in different parts of the image. They're no longer just looking at this one point, they're looking in different places. So where are they actually looking? Now I'm just going to look at the dynamic scenes. In the DM data, we were able to predict where you're looking just by finding change in the image, finding the points of optic flow. So here, what I've done is, around each fixation location, I've identified the mean flicker, which is the change in luminance across 5 frames, around that point in the dynamic version. And we can look at it across the different tasks. So here, just looking in the free view, the amount of flicker you have around your actual fixation locations is significantly higher than a sampled location. And these are your own fixation points taken from a different time point in the same video. So we basically shuffle the time. And we do that to make sure that we control for things like central bias. When you're looking at an image like this, you will always bias your attention to the center of the screen over other parts. So we've taken that into account here, and you find that you're still significantly more likely to fixate flicker. Now, in terms of the spot the location, I've split the data in two. I've got first the data before you hit the button to say you've recognized the location, and then I've got the data after you press the button. So, to begin with, look at it before you press the button, you're doing the spot the location task, and this difference between the actual and the sampled disappears. So you're no longer looking at the flicker in the image. You're actually looking generally away to static areas in the scene. But if this behavior here is a kind of default viewing behavior, that when you've got no task demands, you're just going back to free viewing, and that free viewing happens to preference motion and change in the image, what should happen after you push the button is this difference should come back again. And this is exactly what happens. So people are watching the image, they're looking at the static features, and then they hit the button and they go back to looking at the movement again. Now, taking that same idea slightly further, in these scenes, they're all shot from a static vantage point. The majority of the motion in the image is going to be caused by people wandering around the scene. Either people, or you have environmental features like wind through trees, flags, that kind of thing, or traffic moving around. Generally, those are the only sources of motion in kind of street scenes like this. So we wanted to see more specifically, instead of just looking at the points of motion, are they actually biasing their attention towards people? So we used a tool that I built that enables you to track moving objects through the scenes and classify the probability of a fixation being within these moving objects or elsewhere. And we compare that to your gaze behavior relative to the same regions randomly shuffled around the image. So this gives us basically a random fixation baseline, which is this red line here. During free view, you're significantly more likely to fixate people when it's dynamic compared to when it's static. But even in static, you're more likely to fixate people than the baseline. This difference between static and dynamic disappears before you push the button, and then reappears again after you push the button. We notice that this doesn't get down to the chance baseline, it's still slightly higher. And this is because of what happens in your very first saccade. Now, the way we presented the stimuli was we have a randomly located fixation cross. Rather than have it at the center, we put it somewhere on the screen. Now, we did that to see whether or not your first saccade, no matter where you started from, would bring everyone's gaze to the same point on the screen. So if we look at the free view first, what we've got is the probability of fixating people, and along the x-axis we've got the time from scene onset, to 0 going up to 20 seconds. The probability of fixating people is round about chance at the beginning because you're just looking at a random fixation cross. By about the second saccade, you immediately go up and you've got more than 50% chance of fixating a person. And in dynamic scenes, you stay very high throughout the viewing period. So most of your attention is focused on people wandering around the scene. In a static scene, your first gaze goes to people, and then your interest decreases over time because the people essentially aren't doing anything. The image is not updating. This is the spot the location before they push the button. You find exactly the same pattern. The first or second saccade goes to people in the scene, and then it's like they go, oh, wait a minute, that's not my task. The actual task instructions kick in, and they go down to chance baseline. So the first decade seems to go to the people, and then they start doing the spot the location task. And here, you can see this is what happens after they push the button, where these are the people who've pushed the button very quickly, and once they've done that, the probability of fixating people is back up and significantly higher than baseline. So the gaze snaps to the people, and then they go to the actual background. And I can show you this with very complicated videos. So we've got the 4 conditions. This is free view, this is spot the location, this is the static scene, and this is the dynamic scene. So to begin with, why don't you just watch these 2 up here. And what you're going to see is a heat blob for every gaze point when they're just viewing the static scenes. Actually, sorry, no. Look at these 2. So the free view down here. So they're doing no task, they're just watching the scenes. So you can see that the gaze immediately went towards the centre on both of them, and then fixated these people in the foreground. There's a lot of variance in where people are looking in the static, but in the dynamic, people tend to cluster around people as they come into or out of the frame. Now if I restart it, what's going to happen in these is they start off blue, and then as they push the button, their blob is going to go red. So what you can see is, where do they look when they're blue, and where do they look when they're red? So the red is now after the response. So immediately after scene onset, they all came down and fixated these people. The blue people went up here and looked at the background, and then after that, the red people just start looking at the people wandering around. So you can see the shift. Play it again so you can see it. So immediately the blue went up here, and then it went down to the people. So they're looking at the center of the screen and near the people, and then they're going up, and they've got the task inferences on the gaze, and then they're coming back down and finding the people. So it does seem to be the case, that your gaze behavior can be significantly altered by viewing tasks, as long as that task prioritizes static features in the scene. Now, we didn't tell people to not look at the motion. We told people to do a spot the location task, and they formalized themselves that in terms of finding the actual static features of the scene. But these first few saccades may still be predicted by motion. So now, to go on to the second study quickly, what we're going to do is a different way of looking at the relationship between the visual features and where you're fixating in scenes. We're going to actually manipulate the visual features in the video and see what influence it has on your gaze behavior to see whether or not the features are actual causal in guiding your attention. So we do this by taking very short film clips. Here we're just using 3-second film clips. We'll look at your immediate gaze to the images. And we selectively knock out certain features. Now, the 3 features we chose to knock out were luminance contrast, which is this difference here, when we equalize the luminance across the image to be the same as the mean. So you can see that these dark areas have now become brighter, and there doesn't seem to be any kind of contrast across it. We also knock out edges by doing low-pass filtering. So we let, let's see, this one has got no edge information, so it becomes blurry because we get rid of all high spatial frequency information. And we can also knock out motion. You can't see it here because it's static, except for her arms become blurry, as do the back of her feet. So any bit which is in motion, the frames are being averaged across 5 frames. So it creates this kind of like temporal smearing. So we can take away the rapid motion in the image, just in the same way we've taken away the high spatial frequency information. And we can cross all these to create the final, fully knocked out version. We've got no contrast, no edge, and no motion. Now, if these features individually are causally related to your gaze behavior, by knocking out each one of these, like motion, we should have a significant effect on your gaze behavior. If they're not, then their effect on your gaze behavior should be minimized. So what do these look like? Well, this is one of our clips. All of these clips had people in them, because most of the studies that have been done in dynamic scene perception have had people and they're an easy source of motion. And this is what happens if we get rid of motion. So you can see that when it's static, you can see what the content is, but as soon as it moves, it blurs. This is what happens when you get rid of edges. There's a little bit of pixelation there, which shouldn't be there. It's blurry, it's like you've got something in your vision. And this is what happens when you get rid of contrast. And this is what happens when you get rid of overlay. So there is still something there, but we've actually selectively knocked out these three different visual features. So whilst participants were shown these clips, we had 400 clips across all these 8 conditions. They were shown the clips and they had a cover task which was to rate how much they liked the clips on a 1 to 4 scale. And we weren't intending to look at the preference, but nicely it actually shows behavioural differences. And I'm going to walk you through this because it's the way that we're going to look at the rest of the data. So what we've got is going from the right, this is the fully intact condition. We've got contrast, edges, and motion. And at the opposite extreme, we've got no contrast, no edges, no motion. This is the last video I showed you. And in between, we've got all of these that have no contrast. All of these have contrast. And then, for instance, this one has no motion, this one has no edges, and then the crossing of those. So this is the preference rating people gave us. And what's immediately apparent from it is the minimal impact changing the contrast seems to have. That if they've got contrast or if they don't have contrast, there doesn't seem to be much of an effect on their ratings. There's actually a significant difference here, but it's tiny. If we compare that to knocking out motion, you get quite a large impact. People don't like it so much. And if you knock out edge information, you get the most significant decrease in their rating. So edges seem to have the biggest effect on people's rating of the videos, followed by motion, followed by contrast. So that's how they rate them. But what we're interested in is how they look at the scenes and where they look. So this is the gaze behaviour of our 24 participants watching the original scene. They start in the fixation cross, they all go up to the guy's face, and they track it as long as it's on the screen. And this is the same behaviour you see across all of our clips. They all have one or more people in them, and the gaze behaviour first goes to the people in the scene, and then it goes off and explores around. This is the gaze behaviour at the fully knocked out condition. You can see that it's very sluggish, and it doesn't seem to quite get to the guy's face. The guy's face is here, but there's so little visual information there that they just seem to be going on wherever this blob is that's moving. And this is without any motion and without any edge information. They're very similar gaze patterns, but there's slight variations in the timing and where they end up looking. So we can quantify this by actually looking at the differences on gaze behaviour. So the first one we're going to look at is fixation duration. So when you've got a fully intact clip, you have an average fixation duration of about 350 milliseconds. If I knock everything out, this goes up to close to 500 milliseconds. So you're really sluggish and actually orienting to the content. And this kind of, if we look at then knocking out motion, you have a significant increase, you're slower to orient, but not as slow as if we just knock out edge information. So making it blurry, doing a low pass filter, seems to have the biggest effect on how quickly you orient to the content. And this impact of blur has been shown in static scene viewings before. The fixation duration will directly relate to the spatial frequency information that you're fixating. So we can see that the biggest effect that we seem to have in fixation duration is edges, followed by motion, and then a very minimal effect of contrast again, similar to the preference ratings we had before. You can see where this impact lies if you look at it over time. So this is the number of fixation into the trial, so your first fixation, and this is the fixation duration. And we've got all of the 8 conditions down here in different lines, and rather nicely, they line up in the other direction. So black down here is your normal viewing condition, and you can see you start off with a slightly longer fixation, and then after that, they get quicker as you go through the trial. Now this purple line here is when we just knock out contrast. Has almost no effect on your fixation duration. But knocking out any of the other features and knocking out all three features has a big effect on the duration of your very first fixation. But by the time we get to fixation 6, there's no difference anymore. So it's like you've recalibrated your gaze for the actual visual features of the scene. And all these conditions were shuffled together. So when a scene started, you didn't know whether it was going to be fully intact or whether everything was going to be missing. So you had to look at the scene, make sense of what the visual features were, and then shift them. So I'll skip over saccade amplitude. Now we want to get on to where you're actually looking in the scene to see whether you find the same point when we knock out features compared to what we had during the fully intact condition. So we're first going to look at this in terms of the gaze clustering. And just to confuse things, I've represented it as a slightly different measure. This is the entropy of gaze, where if everyone's looking in the same point, you have a very low entropy. It would be a very peaked distribution of your gaze. If everyone's looking in a space with a large variance, you get a high entropy. Or if they're looking in different points, you get a high entropy. It essentially computes in the same way that we had before. So the lower the value, the more consistent people are in their gaze. Now, contrary to what you might predict, in the fully intact condition, people have a higher entropy. So there's more variation in where they're looking than if we knock everything out. But this is because there is a central fixation cross. And we've already seen that they're slower to shift their gaze around the scene, and they don't explore as much of the image. So they tend to just stay near the screen center, meaning that there's less variation between the gaze. And the only difference we have in terms of the entropy is the only effect that's interesting here is that when we knock out contrast, it has no effect on the gaze entropy, but all of the other features, motion, edges, do. So this seems to suggest that they are differing in the way they look at the image. And we can look at it over time, so that this is when they're looking at the fixation cross, and they have very low gaze entropy here. And then this is time in frames, so by frame 10, which is 400 milliseconds later, which is going to be probably the first saccade, what's happened in the dotted line case, which is the fully intact condition, is they shifted their gaze to the first focal point in the image. And this is the most clustered they're going to be throughout the rest of the viewing time. And then over the rest of the time, the gaze entropy increases as they go off and explore different places. So their first saccade takes them to one point in the image, they stay there for a bit, and then they go off. And in all the other conditions, such as this one, which is the fully knocked out condition, it takes them a lot longer to shift to that location, and then they don't go as far in the rest of the scene. So they're delayed in getting to this point. But where is that point? In pretty much all of our scenes, the focal point of the scene, the thing that seems to capture attention, is people's faces. And they shift from the fixation cross, go straight to a face, and then they go off and explore the image. And this is exactly the same as we saw in the TV clip that we had at the beginning. Whenever there's a face on the screen, snap straight into the actual face, and then shift in between them. So the actual presence of the human face seems to be very important for actually changing the gaze behavior and creating these clusters. And this is not an observation which is new. A lot of my research is actually applying these kind of methodologies to understanding how we perceive and represent film. And Alfred Hitchcock is saying that actually his principal task as a filmmaker is just the organisation of these oval shapes in the rectangle of the screen. If you look at any film or TV, probably about 95% of the shots are about the human face. So most of the stimuli you're going to get in these kind of studies are actually going to have lots of social content. So looking at that question specifically, we put a region of interest around every face in our scenes, and we calculate the probability that every fixation is in one of these face regions. If we look at the fully intact condition, you're significantly more likely to fixate faces throughout the viewing time than will be predicted by chance. And if we knock all the features out, you're just at chance level. So you're not finding the face in the scene. But what's interesting is if we look at just knocking out the motion, now remember motion was the feature that was most predictive of fixation behavior in free viewing, but not in the DM corpus. But here, when we get rid of it, it has no impact on your ability to locate the face in the scene. What does have an impact is knocking out the edge information. If we get rid of the edge information, you're significantly less likely to find the face in the scene. Contrast has no effect, motion has no effect, and anything which is combined that still has the edge information, you're finding the point of interest in the scene. So what I think is going on is that in order to compensate for the visual the visual knockout that's going on in these images, is you're using semantics and rapid kind of gist processing of the scene to identify what you think is the scene is of and where the people are, and you're getting face pop out. So when you identify where a face is, you draw your eyes to that and you use that to kind of anchor your gaze for the rest of the presentation. And this is an extension of a long literature in face pop out, where if we have faces in simple arrays during visual search, you'll be more likely to locate the face than other targets. If there's faces in static scenes, that occupies the majority of your gaze when you're actually looking at them. And even when you have tasks, it's quite hard to change that tendency towards faces. And if we have a static CLT model, and we add a face detector, all of a sudden the predictability goes from like 70% up to about 85 or 90%. So a lot of your gaze behavior in these scenes seems to be accounted for by your social, the social significance of features in the scene. And so the reason why we get this this pattern of behavior is because only in the scenes where we have edge information is the detectors we have for face information is able to actually kick in. Because a lot of the information in faces come from high spatial frequency information. So when we see that information, we're able to locate it and shift our gaze to it. Knocking motion out doesn't get rid of the actual features of the face that we can orient to, unless that face is also in motion. The reason why our gaze may be predicted by motion during other scenes is because the motion that we find is generally caused by the human body. We have sensitivity to biological motion, and that biological motion tells us where the faces are most likely to be. So we can use this information to reorient to the scene and try to find what we think is of interest. So here, if we get rid of the motion, you still lock onto his head. You lock onto various versions of his head, because it's smeared in time, but you're still looking in the same place. And this task wasn't a find the face task. This was a judge how much you like the video task. It's still people are biasing towards the faces. So to wrap up, what I've shown is that the gaze behavior in dynamic scenes is highly predicted by motion and dynamic features in the scenes during free viewing, but if the task overrides the sensitivity to those dynamic scenes, you will actually be able to mostly guide your attention away from it, except possibly for the very first decade. And we can knock out visual features, and as long as we preserve edge information, you're likely to find the point which is most interesting in these social scenes, the human face, and use that to compensate for the rest of the changes. Yes, you'll be slower in orient to it, have longer fixation durations, explore less of the image, but as long as you can find the face, you will still look at it and fixate in the same part of the image. Now, to understand the role of the facial features, we're now following this up by doing comparisons with non-social dynamic scenes to see whether by removing the face, we can actually change the overall gaze behavior. I was going to show you a little magic trick to wrap up, or we can skip to the end. What do you want? It'll take about 4 or 5 minutes. Okay. So I've gone in and deliberately manipulated the visual features and deliberately manipulated the viewing task and shown that it can impact your gaze behavior in dynamic scenes. But this is actually something that I don't need to manipulate because it's happening in everyday life. And a good example of it is what magicians are doing in order to manipulate the way that you interpret what's happening in front of you. So now that I've given you a lot of background, this probably won't work. But I just want you to watch this video, and then I'll ask you questions afterwards.
Using some playing cards. I'm going to deal cards face up onto the table. Your job is to count exactly how many red cards are dealt. Let's see how well you can do. One card left. It has a blue back, but is it red? So, how many red cards did you see? 10? 50? In fact, there are more than that. All of these cards are red cards.
Did everybody see how the card backs change colour? What happened?
No, I just saw them change.
Pete Lamont, is a colleague from Edinburgh, is a magician and a psychologist, and he created this trick because he wanted to show how your assumptions about how tricky magic can be could actually limit your ability to spot it. And he would do this live at magic conferences, and the magicians would come up with these fanciful interpretations of how it happened. But if I show back with the gaze behavior. So if I show this to participants and they move their arms, which isn't a thing, the first time they view it, the cover task makes you think that you're counting the numbers of the cards. It's obvious, it's what you do in most tasks. So when he actually starts laying them out, it's quite a fast little action, so you have to attend down here in order to see the number and the colour of the suit. So people attend down here. And when we do this on the eye tracker, this is about 3 degrees, 3.5 degrees of visual angle. And halfway through, the cards just change from being blue to red. When he does the reveal at the end, he basically drops those that have the blue back, and he just shows the ones that have the red back. So it's a very simple trick. And it's a sign that the dynamics of the scene and your expectation about what's relevant influence where you fixate and what you represent. So these kind of manipulations of viewing tasks are going on and are actually kind of personally devised as you're attending to complex scenes like this. So when we show this to participants, and we ask them after the fact, did you detect where the red cards appeared? And here we just have 8 participants. None of them were able to actually detect the change in cards. So I wanted to break it. So we try to use visual salience to actually undermine the magic trick. So about 250 milliseconds before the card backs changed colour, I inserted this rather large pink outline which appeared on the cards. So if their attention was being captured by this, they should saccade up to it, and they should be there when the card backs changed colour. We found that none of the participants noticed the flash, and none of them detected the card back. None of them fixated the onstone. So if I give them a dual task, when I tell them about this flash, they have to count the number of cards and they have to push a button when they see a flash. They don't know what it's going to look like or where it's going to appear. Find that 7 out of 8 of our participants were able to detect the flash accurately. 4 out of 8 even saccaded to and fixated the dealing hand after the card backs changed colour. None of them noticed the card backs changed colour. So what they were fixating and also what they were representing was massively related to what they thought was relevant in this task, just due to the dynamics and the actual instructions the magician had given. So that kind of wraps the different factors of the presentation and the things that influence your gaze behavior in dynamic scenes up. And generally, what we find is that attending to a dynamic scene involves reconciling your interest and your viewing task with the dynamics of the scene and the factors in it that may capture your attention. Motion is a very strong predictor during free viewing, but task can bias you away from motion if the task is actually specified appropriately. But quite interestingly, the edge information in the scene may have the greatest causal impact, although this may be due to social significance and the features which are actually which are revealed by the high frequency spatial information. And we're going to try to see if we can manipulate that in practice. And so what I hope to have shown you is that dynamic scene viewing can capture the active interplay that we have with the visual stimulus and the world around us in order to get at a more naturalistic engagement. Thank you. Good time.
Anybody has questions?
Surely Simon has a question.
Started early.
So your point about faces is interesting. So you made an observation that 95% of films have faces in them. My guess is that that statistic is probably true for kinds of things we make dynamic in movies and experiments. So I guess there's a question then about to what extent does it really reflect social significance just versus the statistics of the environments that we created or experiments.
So the familiarity with content presented like this and the statistical regularity and nature of the actual presence of the faces. I think it's very hard to dissociate that because, say, if you posed it as a developmental question, like what is the completely naive gaze behaviour of an infant, a newborn infant on the world? They found that even within a few hours of birth, they're biased towards faces, and it's hard to dissociate whether or not that's already seeing the statistical distribution and regularity of faces in the visual field, or pre-existing genetically derived face processing. I think that when you apply it in this domain to neurotypical adults that are looking at a video on a computer screen, right, the majority of what they see will have been face-based material. So that's why we're trying to get rid of the faces in the stimuli whilst preserving these focal points of motion. So we're trying to find stimuli that could actually dissociate those two and still see if people are actually being biased by the visual features. But I think that's an interesting question, and I think if we could actually capture the statistical frequency of certain objects in stimuli like this, then that would actually become quite a good semantic predictive model of gaze behavior. And so far that hasn't been done. You could think of that being kind of the scene equivalent of corpus, textual corpus predictions of gaze behavior, where we can actually relate to where you fixate to the frequency or the complexity of words in the corpus as you experience them. We don't have anything from the scene side that can do that.
I guess the faces for the infants are not really static either, are they? The animals move.
Yeah.
And they're also coupled with other sensory information, audio and things like that.
And it's made extreme, so we actually emphasise that as much as possible.
Yeah. And actually, no people in scenes here are usually coincide with actions that we endure. So, it may not just be faces, it may be that the principal agents.
So we've used a range of clips. In the DM project, it was all kind of found footage, so they'd all been composed to enable you to actually see what's relevant or what the director thinks is relevant in the image. So the lighting, the framing, all these things point towards usually the person's face. In the video clips I used in the spot the location task, we put the camera down and we tried not to frame it. So we did it relative to the background and then people just wandered in and out of shot. So there wasn't anything in the visual features which should have been biasing you towards that, except for the fact that they are doing actions and they're basically correlated with all these other things, with the low level and also the semantic interpretation. So we have some video clips where we've actually got where the people are the least interesting part of the scene. So this person just sat there on a bench not doing anything, and you have traffic and things going on in the background. And if we get more clips like that, then we can maybe actually start to see, does that override the visual sensitivity?
And does it for that one picture? Because you've recorded quite a lot of participants.
Just looking at the few examples of that, it doesn't seem to. I think that if you had a high point of motion immediately after scene onset, and you had a person that was equidistant from the fixation point, then your gaze would probably go to the motion. But then within a couple of saccades after that, you'll find the person, and that seems to be during through you. I haven't looked at it at that level in the spot location test. I could drive it down and see.
So what would happen? It's actually very hard to imagine something that has diagnostic movement that isn't relatively human. I mean, I suppose there are animals and so forth.
Yeah, we're using animals mostly, because we need to find clips that if you're freeviewing, you do all look in the same point at some point during the clip. If I have a panning camera where the entire scene is moving, then you don't get attentional synchrony. People will be off looking at different parts of the image. The only scenes that we found that you do have these kind of clustering of gaze is when like natural nature documentaries. And so we're using clips where non-primate animals, so that sensitivity to human motion and faces can't kick in. But I think even then, we have such familiarity with animals and recognition of their motion that then other factors may come in and actually guide our attention to them. But we're just running it right now, so we'll see. But this is the interesting thing is that if you say what is a dynamic scene, it's a scene which is either made dynamic by our changing viewpoint and our movement through it, or objects in the world moving relative to a static vantage point. If we're static and things are moving in the world, then they're pretty much always agents. It's either an animal, or it's a person who is influencing the movement of something else, like a pushchair or a car. So the motion always has semantics relative to a static reference. So when you see motion, it's very hard to have that where it doesn't already have some semantic interpretation, or at least prediction of what it's likely to be. We are also doing studies like this with non-naturalistic scenes. So we're, in the same way that we stripped away the features from the visual scenes, we're finding other ways of representing motion and edge information without having all the other realistic features of the scene. So getting more kind of down to the basic level of the visual features and the relationship to gaze. And then you become a lot more predictive in people's gaze behaviour if you just have a high point of motion. But then it's just like a visual search task.
So sorry to go on about this. It's very interesting actually. So do you ever run these sorts of experiments on, for example, prosopagnosia consultations?
I haven't, but it would be very interesting because the face detector seems to be so resilient that even in the complete knockout conditions, so that one, the one on the left, isn't a good example because at some moments his face is stable on the screen and all of a sudden it just comes into sharp focus, and so you latch onto that and then you track the blob. In the no edge condition, it's probably the biological motion and also kind of skin contrast, which is giving you a sense that it's probably where the face is likely to be. If we have someone who's prosopagnotic, didn't have that sensitivity, then their gaze would probably be a lot more predicted by motion. We've run similar studies on infants. If I look at the gaze behaviour of a 6-month-old, their gaze is much more predicted by visual saliency and motion than it is by face information. By about 12 months, they're actually starting to become more biased towards faces in a whole-like way. So as the social familiarity and sensitivity to faces increases, so does its apparent ability to inhibit sensitivity to motion or facilitate towards faces. So looking at it in various different ways. Monkeys do the same thing. data primate studies comparing gaze behaviour of chimpanzees to infants, and you find that actual chimps have bias towards human faces and chimp faces in a similar way, although they're more predicted by visual salience than human adults are. It's interesting to find populations where you can knock out that semantic significance.